Okay, so I'm happy to introduce Professor Zhunga Liu from Northwestern Polytechnical University. So Professor Liu has done a lot of work on belief functions. It's one of actually the top researchers on belief functions, and especially with applications to machine learning and information fusion. And today will give us a lecture about the application of belief functions to classification or pattern classification. Okay, so please, Zhunga, you can start.
Thank you, Thierry. I'm very honored and pleased to present some work about the pattern classification with the belief functions. I'm from Northwestern Polytechnical University, and this is in the Xi'an, China. It's a pity that I cannot go to the Japan to attend. In fact, I want, but because some lectures in China, so I cannot go there. Okay. This is the outline. I will introduce some basic knowledge and some typical evidential classifications at first. Then I will talk about some recent development about evidential classification and briefly introduce some of our work about that. As we know, in the traditional pattern classification, they tend to perform the data set with some assets. In fact, usually they will classify the object into some particular or specific class. For example, we can see there is three classes, omega 1, omega 2, and omega 3. For the hard classification, usually the object will be classified into omega 1 or omega 2 or omega 3. If some object lies the overlapping zone, for example, like this gray zone, it is difficult to be clearly classified. In such case, we think maybe this cannot be clearly classified because of the insertion, because the used attributes may be not sufficient for the class. In such case, we prefer to put it into the meta class or the set of class, for example, the set of omega 1 and omega 2, rather than put it into a specific class. Because if we put it into a specific class, it may be cause the error with very high risk. Usually we consider the imprecision can be better than the error in some case. And we know the belief function theory provide us very good framework to characterize such imprecisions. Okay, and this is the basic knowledge about the belief functions. As we know, we can see the power set. The power set will characterize the imprecision of classification. For example, the set of theta 1 and theta 2 will reflect the imprecision of classification between these two classes, the theta 1 and the theta 2. So we want to, and many researchers have done such work about classification with the belief functions. Okay, we will skip such, I think, skip such slides. And the belief function, the possibility functions. Okay, this is a Dempster rule. This rule will be used in the classification. So, okay, I will introduce some typical evidential classification. The first one is this is very well known about the evidential k-nearest neighbors. And this is proposed by Professor Denœux in maybe almost 30 years ago. It is very simple, but very effective in many cases. And for example, to be classified, usually we will find these k nearest neighbors. And for each neighbor, we can get a BBA, a simple BBA. For example, if this neighbor belongs to class omega s, we will construct such BBA. The object will be considered belong to the omega s, and also some other mass will be committed ignorance. This is very simple BBA for each nearest neighbors. So this is also very easy to understand. If the object is very close to this neighbor, okay, it will be committed the bigger mass on the class omega s. Of course, if this object is far from the neighbor, okay, the less mass will be committed to the omega s. And the other mass will be committed to the ignorance. Okay, so the sum is equal to 1. And then we can get k BBA, such simple BBA. Then the object will be classified according to the fusion of the KBA. Of course, the KBA will be fused by the Dempster-Shafer rule. In the evidential k nearest neighbors classification, it takes into account both the distance information and also the uncertainty of the data. Uncertainty can be characterized by the ignorance data element. Nevertheless, we find there is a particular case if the object is very far from the neighbors. For example, if one object is very far from the training data, usually it should be considered as the outlier or noisy data. However, for such simple BBA, for example, if one object has k nearest neighbors all from the omega s, when the k is very big, then we combine them using a Dempster rule. Usually, most BBA will be focused on the omega s. The bigger k and the most belief will be committed on the omega s. So it is difficult to classify this object into the outlier. So such other some other version of the evidential continuous neighbors are developed. For example, this one we allow to classify object into the meta class, like the sets of the class. For example, for each object or target x, and we propose another method to construct the BBA. For example, the basic principle is like that. For example, this point represents the object. If it is very close to a neighbor, for example, this is the threshold. If the distance is smaller than this threshold, it will be considered okay. This should belong to the same class as the neighbor. If it is quite far from the neighbor, for example, the distance is bigger than this, okay, it will consider that it cannot belong to this the same class of the neighbor. If the distance lies this zone, the imprecession zone, we will consider is uncertain. It will be determined by combining with some other neighbors. So we propose to construct the BBA using the two functions. The first one is determine it belongs to the omega s. The second one is about it belong to other class, not the omega s. Then we will combine the two sub BBAs to obtain the BBA about the object belong to omega s or not belong to omega s, and also another element about ignorance is also taken into account. And then we can, this is the flowchart of the method. If the object, the BBA is associated with the omega 1, for the BBAs associated with the omega 1, they will be combined with the DS rule. This is a simple DS rule. If the BBA, for example, this is the fusion result, they associate with a different class, then we will combine them, use like the DP rule. This is in order to preserve the conflict beliefs, to reveal the imprecision of the classification. So by doing this, we allow to assign some object that is difficult to classify to the meta class or the set of class. Of course, if the object is very easy to classify, it will be committed to the specific class. And if the class is very far from other class, in such case, most belief will be focused on this focal element cannot belong to A. In such case, it will be put into the outlier or noisy class. Okay, we just simply introduce the typical class. In fact, there are also some other class, like the evidential neural networks, and this can be considered typical evidence class. In recent years, we also do some development about the evidential classification. I will give a brief introduce. The first one is about the evidential classification of the incomplete patterns. In the practice, we often encounter that the object with some missing attribute data. For example, usually a pattern or an object is represented by a vector, maybe 10 or 20 attribute data, but there may be a few of the part of them maybe just contain 8 or 5 attributes. The other 5 are missing. In such case, it will cause the classifying result very uncertain. In the previous work, usually they want to classify such patterns with a missing value into a specific or a particular class. In such case, we think this is maybe not very reasonable, because the error risk usually very high. So I think maybe we should put into some sets of class to use the imprecision to reduce the error. So we propose a method with the adaptive imputation of the missing value. For example, we can see this figure. If the x of this pattern contains 2 dimensions, x and y. If the x is missing, we just classify the object according to y value. We will see the green circle points cannot be classified between the class A and C, because they are overlapping according to the y value. And also the red square points cannot be classified between the class A and the class B. Class M. And the red star and the black star and the blue star, these points can be classified. So we can see if the missing data, the missing value, sometimes they play very important role for the classification. For example, for these green points and for these red squares, the missing value is very important for the specific classification. But for the stars, or red star, dark star, and black star, and blue star, in fact, the X value is not so important. We can still obtain the very specific classification without the X value. So the influence of the missing value usually depends on the context. So we will present the method with the selective or adaptive imputation of the missing value based on the belief functions. First, we will classify the object directly using the given attributes. For example, for these star points, we will directly classify using according to the Y value. If the object cannot be clearly classified, in such case, we will consider missing value is very important for the specific classification. In such case, we will impute the missing data. For example, like the circles, the green circles. We will estimate the missing value. Then we will do the classification after the estimation. So in such case, the creative classification allows the object to belong to a specific class and a set of class. If the missing value cannot be very correctly classified, in such case, we will allow such green points belong to the class A and C, not only to A or C. We belong to a set of class. This can reduce the errors and also represent the imprecision of classification. Okay, this is the flowchart of the methods. First, the direct classification of the income pattern. We will just design a very simple classification method to classify the patterns with the known attributes. We just ignore the missing value. We just use the known attributes to do the classification. Okay, if we can get a very specific classification result, it means the distinguishability degree is high. We will consider, okay, this can be clearly classified, and we will not do the imputation of the missing value. In such case, we will directly get the output by simple fusion. If we find the classification result is very uncertain, in such case, we will do some most complex imputation to imputation the missing value based on each class, and then we will do the further classification and of course the weighted classification. I will explain in the sequel. Finally, get the fusion result as the classification. By doing this, we can reduce the computing burden, because some patterns the missing value is not very important. We can directly get a specific classification result. If the missing value is very important for the classification, okay, then we will do the imputation. We will not, we do not need to do the imputation for every patterns. Okay. This is the details about the method. For example, let's test the data, the object, and you classify using the training data. Okay. First, we will get a prototype of each class. For each class, we can get a prototype using the training data. This is very simple, just the average value of the each training data, training class. For C-class problem, we can get a C piece of simple classifier result according to each class. Okay, for one object, we can get a classifier result according to each class. If this object is very far from the prototype, okay, the mass will be small. If it's close to this prototype, the mass will be bigger. This is very similar to the evidential KN method. Okay, for the simple vector classification, then we will get indistinguishability degree of the object associated with a different class. We use this, the comparison between the second one and the max one. The max one is max mass means this object is very close, the most close to the prototype, and this is second most close to the prototype. Okay, if this degree is smaller than given threshold, if it is smaller than the threshold, it means this two value is very it is smaller than the threshold, it means the two values are quite different. They are not very close or not very similar. In such case, we consider that the available attributes or the known attributes are sufficient for the specific classification. And then the CBBAs of CBBAs like that, the CPs of the BBA associated with different class will be directly combined by the DS rule to obtain the final classification result. Otherwise, if it is bigger than the threshold, it means the two values are very close or very similar. In such case, the two classes cannot be clearly distinguished. So we will move to the next step to do the imputation of the missing value. In the estimation of the missing value, because it is in fact very difficult to do the very accurate estimation. So we use the SOM self-organizing map technique to do the estimation. For example, the SOM is applied in each training. SOM is a clustering technique. And like the fuzzy C-means, it will be applied in each training class. And we will get M product N nodes. And then we will select the k nearest nodes to impute the missing value. Because the training class are usually considered with without missing value, they are complete. So the k nodes are used to k nearest or k select nearest nodes are used to estimate the missing value. And of course, the k nodes have different contributions in the estimation. This is if the node is close to the object, it will be considered play an important role in the estimation. Otherwise, it will play a smaller role in the estimation. So this is the weight of each node in the estimation. And this is distance. The big distance, it means a smaller weight. And the weighted mean value of the second nodes will be used to fill the missing value. The keynotes, they have the complete attributes, and the weighted mean value of the select keynotes will be used to fill the missing value. In fact, the missing value will be, this is the estimate of the missing value. By doing this, we can get C versions of added pattern according to each train. Okay, this is a C training class. We consider C class problem, so we can get C versions of the added pattern according to training class. And each class have the, in such case, the added pattern have the complete values. There is no missing value. And they will be respectively classified based on each training class, just as the previous method. Okay, we will classify it according to prototype. If it's smaller distance with the prototype, okay, it will be get more mass value on the corresponding class. This is a very simple classification. And then the C piece of results will be used to, because the C piece of classification results may have the different weighting in the final classification. And the weighting factors of the C piece of classification are defined by the sum of the K SOM nodes. Okay, it means because for each class we select K nodes. Okay, if the object is close to this class, okay, this corresponding class result will be considered with a bigger weight. If it is far from the another class, okay, this class, the class result about this class will be considered with a smaller weight. Okay, finally, we will get the relative weighting factors, relative, and we consider the class result with the most close to the class. This weight will be considered equal to 1, and the other is smaller than 1. Okay, after that, we will get the discounting. The C piece of class result will be discounted by the relative weighting factors. And these discounted value will be combined for the final classification. In fact, this is also like the DP rule. If the conflicting beliefs is bigger, it will be kept, will be not redistributed to other specific class. By doing this, we want to classify some objects that is not easy to classify to the meta class, to the sets of class. Okay, this is some experimental result. This is we can see this is the Y values are missing. We just classify the object according to the X value. We can see these. This is the traditional method, FCM imputation. This is KN imputation, because in such they do not allow to the object that belong to the set of class. In our methods, we can commit some object that is hard to classify to the set of class, the class omega 1 and omega 2, the class omega 1 and omega 3, and so on. Okay, this is some using some other often used data set, open data set. We can see we can reduce errors, but of course it causes some imprecision. So we should find a balance between the errors and the imprecision. Okay. The second one is about evidential transfer classification for the heterogeneous state. In recent years, we know the transfer classification develops very fast, because in the pattern classification there is a challenging problem. It's about the pattern classification without training patterns or labeled patterns. Usually, if we have a lot of labeled patterns, usually the classification is not very difficult. But if we have very few or even no labeled data, then we want to do a good classification. This is very difficult. And in many applications, there may exist some label data in some other related domain. And such label data can be helpful and useful for us to solve the classification problem in target domain. For example, we want to do the classification, for example, some ships in the sea, and we just have some label data from a satellite, but the object to classify is obtained from some, for example, from planes. So the data from the plane may have the different distributions as the data from the satellite. But we do not have enough label data from the plane. We just have a lot of label data from the satellites. In such case, if we want to do the good pattern classification or object classification, we just use the data from label data from the plane, maybe not sufficient. So we have to employ the data from the satellite. Maybe this can be helpful for us to improve the classification accuracy. So this is called the source domain and the target domain. Source domain usually have a lot of labeled data, and the target domain usually just have the objects. We have very few labeled data. So we want to take advantage of the complementary knowledge from the source domain to help us classify the object in the target domain. In previous work, the object in the target domain and the patterns in the source domain usually will be mapped in a common domain, in a common feature space, to make their distribution becomes close. In the previous work, each object in the target domain usually have only one mapping value in the corresponding or transferred domain. But we know if the data is heterogeneous, the mapping may be very uncertain. Usually, maybe the values in the target domain are very close, but in the source domain, maybe they are very different. For example, some some data, some patterns in the random image, maybe they are very close, but in the optical image, maybe they are quite different. So this means the mapping or the transformation may be very uncertain. How to deal with such uncertainty, in fact, is not very easy. Very easy. So because so we want to develop a new transfer classifying method for the heterogeneous state based on the evidence theory. We want to use the big functions to deal with such uncertainty. And the first is the estimation of the missing value in a source domain. We do not miss the exact one missing value. We just estimation a scope. The missing value scope contains multiple mapping values. And then we will determine the mapping value in the source domain and then classify the mapping value based on the evidence theory. In this transfer classifying method, the most important is that we allowed to estimate the mapping value, the mapping value of the object in another domain with multiple estimate values, not only one. For example, the object in the random image is only 1 pixel. Then we will transfer it to the optical image. We allow to transfer it into multiple value, not only one value, because the multi-value will characterize the uncertainty of the transfer. If we just estimate only one value in the optical image, it may cause very high error risk. Okay, for classification, we first need to transfer the object to the source domain using the labeled patterns. Because the source domain and target domain are heterogeneous, it is difficult to directly obtain only one exact value from for the object in the source domain. When the patterns in the source domain, so we will divided the patterns in the source domain are divided into multiple clusters by SOM. Of course, you can by the FCM, some other clustering technique is also okay. And then we will find the nearest cluster of X, which is defined by that. And the actual mapping values of the pattern is developed, is denoted by sets, not one. For example, one pattern, we will find the nearest cluster, not the nearest neighbors. We just find the nearest cluster. This cluster may contain a set of patterns, not only one. So we think this multiple mapping value can represent the mapping value of this object. If we just use only one, it's not sufficient. Okay, we will see this this figure. For example, this cluster I and the mapping scope, they are very close. Okay, the blue square in the target domain is close, and the source domain, they are also very close. But for the cluster J, in the target domain, they are close, but in the source domain, they are not very close. You see, the dispersion is a bit high. So in such case, for example, for the blue points, okay, we think the clusters in the south domain maybe only one value is okay. We just find the average value can be used as the estimated mapping value. But for the green one, I think the only one mapping value is not sufficient. Maybe we need to use a multiple mapping value, because you see this is the star and the twinkle are very different. So we at least, in such case, we need to find two mapping value to represent these clusters in another domain. So the mapping between the heterogeneous domains may be very uncertain, and the estimation uncertainty and about the mapping value can be represented by the standard deviation. So we use the standard deviation to calculate the mapping values. Of course, if the uncertainty is small, the threshold, okay, we will just use the average one to use as the mapping value of the object. If the uncertainty degree is very high, we will use multiple mapping value to calculate this transformation. Okay. Of course, if there is only one mapping value, this can be directly classified according to the estimate mapping value, because in the mapping domain, in the common domain, we can use the labeled data in the source domain to classify the object, because in this common domain, the distribution will be both, and the distribution of the source domain and the target domain will become close. Of course, this is the transfer learning. They will transfer the source domain and target domain to the common domain. Of course, the common domain can be the target domain or source domain. This depends on the applications. If the object has multiple mapping value, okay, in such case, the mapping value will be respectively classified by the training classifier, because we cannot sure which mapping value is confident, which one is better, which one is not very good. We can, so we just classify using each mapping value. Then the classification result will be combined by the evidence theory. Of course, there is some weighted. The weighted will depend on the mapping value. This is some classification result we can see. If we use multiple mapping values, the classification result will be improved. Is higher. This is the classification accuracy is higher than the traditional method, because the traditional method each object just has only one mapping value in another domain. Okay, this is the application in the remote sensing data classification. For example, we can see the source domain and the target domain. This is the multiple spatial optical image. This is a gray image, and some pixels in the color image are close, but in the gray image maybe not very close. Okay, this is the training data. We just know these pixels are pairs, they corresponding to each other. And we just have some labeled data in this gray image, but we do not, we want to do the classification about the color image. So we want to transfer the color image to the gray image, and then we will do the classification in such gray image. And we can see the accuracy and the kappa coefficient for our method is higher than the traditional method. This is just because we allow the pixels in the color image may have multiple mapping value in the gray image. The traditional method, they just allow each pixel just have one pixel mapping values in another image. So this cannot will characterize the uncertainty of the transformation. Okay, another one is also about the transfer classification, because in the previous work, we just considered one source domain. In some applications, we may have multiple source domain. For example, we as a previous. Okay, we can also see these four figures. We want to do the classification for the target domain, the last one. And then we have many source domain, but each source domain also have the different distribution. This is the first source domain, this is second, this is the third one. In fact, for each source domain, they can provide more or less complementary knowledge for the pattern classifying in the target domain. So we also want to use all the source domains to help us to improve the classifying accuracy of the target domain. So in this work, we considered the multiple source domain. In fact, in some real applications, there's also exists many cases like that. For example, we want to do the classification of the remote sensing data from the plane, but we have some data from the satellite, from satellite 1 and satellite 2 from a different satellite. So for each satellite image can provide some useful knowledge for classifying of the image from the plane image. So we want to take full advantage of all the image data from the satellite. In such case, how to make full use of the different source domain? In the previous work, they usually simply combine all the source domain together. For example, these three source domain will be directly combined together to combine into one source domain. And then we transfer the target domain and the integrated or the combined source domain to a common feature space. However, if we simply integrate the different source domain together, the integrated source domain will have the different distribution with any source domain. This is not very helpful or very useful for us to improve the classifying accuracy of the target domain. Because the combined domain or the integrated domain, in the transfer classification, we can make sure or grant the target domain and the integrated domain as close as possible. But we cannot grant the target domain is as close as possible to each source domain. So this is not very helpful for us to mine the useful knowledge from each source domain. So in order to utilize the complement knowledge from each source domain, we propose a new combination method based on the belief functions for the multi-source domain adaptation or transfer learning methods. Okay, we can see our methods for each target data. This is a target domain, this is a source domain. For each one, we will not combine the source domain together. We just make each source domain and the target domain use the transfer learning to transfer common feature space. Then we do the certain pattern classification or data classification. So for each data, we can get, if for n source domain, we can get n piece of classification result with the help of each source domain. And then we will combine the classification result in the decision level. In fact, we just combine the classification result using the evidence theory. By doing this, we can take fully advantage of each source domain and each source domain to help us to improve the data classification. If we combine the source domain together, you can imagine we just put a target domain and combine the source domain to find a common feature space. In such case, a lot of useful information contents in the source domain will be lost, will be not used, because the combined source domain, in fact, is a new domain. This may be different from each source domain, any of source domain. So we want to make each source domain are transferred, are aligned with the target domain using the transfer learning method. We do this one by one. Of course, by doing this, we will increase the computation complexity, but also we can improve the classification accuracy. And we just combine them in the decision level, just combine their classification result. So for each object, we can get a classification result with the help of each source domain. This is the reconstruction or transfer learning. We can also get the transferable classification result by some simple classification method. After that, in the combination, we also use a weighted combination. For each classification result, we have the different weights. If, for example, if the target data is close to the source data 1, okay, this classification result will get a bigger weight. If this target is quite different and their distribution is quite different, okay, this weight will be small. So this distance is used to calculate the weight. The distance, in fact, this is a distribution distance. If the distance is big, it means the target data and the source data are quite different. Okay, so its corresponding weight should be small. If it's very close, it means this source data will provide a lot of useful knowledge for us to improve the classification, so its weight will be bigger. We will use the distance before matching and after matching, and then we will calculate the average. Then we will use the weight. Of course, this is a relative weight because we consider one classification result, the weight is equal 1, and the discounting result after they will be combined. According to the combined combination result, we will get the final classification result of the object. Okay, so we can see our method can efficiently improve the classifying result, improve a lot classifying result. The accuracy can be significantly improved. Of course, by the price at the price of the computation burden increasement. Okay, next work I will introduce some evidential classifier fusion with a refined reliability evaluation. As we know, the classifier fusion is a very efficient strategy to improve the classifier accuracy. And there also exists a lot of the classifier fusion method because the different classifiers usually can provide the complementary knowledge for each other. So the combination of the different classifiers usually can improve the accuracy. And as we know, the classifiers to combine usually have different reliability. And the reliability evaluation usually is very important and helpful for us to improve the accuracy. Of course, the classifiers the classifier means here can be the classifiers trained by the different attributes. Of course, the classifier can also be used different training data and so on. And the weight of the classifier is also determined by the classification accuracy. For example, in the training data, for example, if one classifier has very high accuracy, usually its weight will be bigger in the fusion. If the classification accuracy is very low, okay, in such case, the weight usually is small. This is the traditional way. But we know if we do this, we cannot efficiently calculate the difference of each pattern. This is just to measure the reliability of the whole classifier. It cannot calculate the reliability for each patterns. For example, for classification, maybe this classifier is very useful or very effective for a part of patterns, but for other patterns, maybe the accuracy is not very high. So if we use the traditional method just to use the overall classification performance to measure the reliability, maybe this is not a very good solution. So we want to develop a method for revising the classifier output by refined reliability evaluation. For example, we want to see for classifier if the classifier usually classifies the object, the class A, misclassify the class A into the class B. Okay, because use the training data, we usually can get some prior knowledge. Okay, this classifier usually misclassifies the A to B. In such case, we can communicate the mass on the class B into the class A, because we know it truly belongs to class A, but it misclassified to class B. If we can get such prior knowledge, we can do a very refined correction for the classifier output. So according to this basic idea, we do some work about that. So we define a very refined reliability matrix to represent the conditional probability of the object belong to omega I, but misclassified to omega j. This is like the confusion matrix. And the given classifier is expected to produce the similar class on the object and its close neighbors. Because we want to estimate the reliability for each object, we can just use the close neighbors of the object in the training data. So for each object, we will find its k-nearest neighbors in the training data. Then we will estimate the reliability matrix according to the classification result of the neighbors. Because the neighbors with a real label, we know it's true label. So we will input these training data into the classifiers. Then we will estimate the predictor labels and compare the predictor label and the true label. We can estimate the errors, the prior bias errors of the classifier. For example, we can see this is the object truly belong to omega I, but it is classified into the omega j. In fact, this is very easily to be estimated using the training data, because the training data we know is true label, and we also put it into the classifier. We can get its predictor label, and by doing this, we can estimate this conditional probability. This is conditional probability. Of course, for each neighbor, because we use the k-nearest neighbors to estimate this errors. So if the neighbor is very close to an object, okay, it will be considered as a bigger weight in the estimation of the reliability matrix. Okay, it is worth note that for each object, we will reliability is corresponding matrix. And this matrix, for each object, it will have a reliability matrix. This reliability matrix is for each object. The different object will have a different reliability matrix. So for each object, we will find its k-nearest neighbors and use the k-nearest neighbors to estimate such reliability matrix. Okay. This is the condition when it is truly belong to omega I, but is misclassified to the omega j. Okay. Then we will transfer it to when we know it, because for the object, for the query pattern, we have no idea its true label. So we just want to estimate its true label. So we just know its estimate predictor label is omega j. So we have to calculate this conditional probability when the object is the estimate, the predictor label is omega j, and in such case the object truly belong to the omega I, this probability. So this can be calculated according to Bayes rule. So very simple Bayes rule. We consider prior probability is equal, so they can be omitted. And by doing this, we can calculate the prior probability about the reliability matrix for the object when it is the predictor label is omega I, but is classified to the omega j. Okay. By doing this, if we get this reliability matrix, we can do the correction of the classifier output, because we know it is reliability matrix, and we can use this matrix to to do some correction about the classifier output. For example, if this is the classifier output about mu j, it means the object belongs to the class J. The probability belongs to class, or the mass or belief belongs to the class J. But we have estimate if the object is the predicate label is omega j, but is truly labeled omega I. This conditional probability is known. So we will transfer the probability, the transfer to the class omega I, to the omega I. But we just do the estimation about the reliability use the neighbors. Maybe the neighbors is not very close, not very similar to the object. So if we directly transfer the probability of the omega j to the omega I, maybe we'll cause some error risk. So we find a compromise approach to transfer the mass to the set of omega I and omega j. This is the imprecession of the uncertain. So such uncertain will be reduced by combining with other classifications. This is a very prudent way for the correction, for the probability correction. If we just directly, for example, according to the basis, we should directly transfer the mass on the omega j to the omega I. But we think this is maybe with high risk, so we just find a compromise way to commit to the set of class. This is like a compromise. So we after the correction, we can see the some mass will be committed to the set of class omega I and unit omega j. Contain two paths. One path is the omega j is transferred to the omega I. Other path is the omega I transferred to omega j. Both paths will be committed to the set omega I, omega j. By doing this, we will increase the imprecession of the classification, but we can also reduce the error risk. Okay, this is omega I to omega I. Okay, this is the specific class. For each class feature, we will do such corrections. After this correction, we can see the classifying output will contain some set of class, will become a bit uncertain. After that, we will do the combination. The combination of the different classifying result from the different class features. Because if, for example, if the object in different classifiers do not make the same mistake, okay, then the fusion will be very useful to reduce the imprecession. For example, in this classifier, omega j is misclassified to omega I, but in other classifier, omega j may be misclassified to omega h or j. If it's not omega I, okay, after fusion, we can find the combination is omega j. We can get the correct classifying result. Usually, the probability to make the same mistake is very small. So by doing this, we can improve the accuracy and also reduce the uncertainty. So this fusion, the classifying result is in the experiment, the result is very good and improve a lot compared with other methods. Of course, this is at the price of the computation burden, because for each object we will calculate a reliability matrix for that. So the computation burden is very high. So if we want to pursue a very high accuracy, we can use such method. So if we want to very real-time classification, maybe this is the computing burden is a little bit heavy. So this method is mainly used to improve the classification accuracy by the refined reliability evaluation. We can see this is usually very, very high, much higher than other methods. And also is very robust to the k value, because the different k usually have different weights in the reliability evaluation. If the neighbors is very far from the object, usually they have small weights, so the k value is not very important in the reliability evaluation, because the neighbors far from the object plays a very small role in the reliability estimation. Okay. In the final, I will introduce another work about the evidential combination with different frame of discernment. In the traditional method, usually we consider evidence are defined in the common frames of discernment. In fact, in some real applications, we will find the discernment frames up. The evidence are from the source of evidence from different frames. For example, the framework 1 is just different animals, or dog, sheep, or fish. And the framework 2, maybe this is a large, medium, small, to represent its shape. This is represent the kinds, the types of the animals. In fact, we can find the evidence from the framework 1 and 2 maybe can provide some more or less complementary knowledge. If we can combine the source from the different frameworks, we can also improve the classification accuracy. But how to efficiently combine the two frameworks, two sources of evidence from the different framework? In fact, it's still a lot of work to do. So in fact, we do some work on that, maybe not very good, but I want to share with I want to share it, and also want to discuss it to show how to efficiently combine the source of evidence from the different frameworks. In our work, we transfer the evidence from the different framework into a common framework. Then we will combine them in the common framework. The common framework usually depends on the actual application. For example, in the application, the user want to get the final fusion result in a framework. Okay, we will use the framework as a common framework, and then we transfer the evidence from the different into this common framework. But how to do such transformation also not very easy. Not very easy. In our work, we we propose a transformation matrix for mapping the evidence from one frame to another frame, and this is given by that. For example, the before the Q elements represent the for example the P is we can see the P is the elements in the phi. The Q is the Q is Q is the P is the elements for the theta. Q is the element for phi. Sorry, this is typos. So this the previous the Q element means the theta 1 to the phi Q, how to redistribute the mass from the theta 1 to the to each element in the phi. And the Q plus 1 and the Q plus 2 means this one means because in the previous we want to transfer the mass on C1 to not only the Q elements but also to the sets, any subsets of the Q of the work. But in such case, the matrix will become very large. It contains too many elements in the matrix. These parameters will be difficult to calculate. As we know, if because these parameters must be calculated using some training data. If the parameters is too many, we will require a lot of parameters. This is not easy to calculate. So we think, according to prior knowledge, for example, if we know theta 1 just is associated with phi 1, phi 2, phi 3, okay, we just consider these three parameters, and this one is a set of phi 1, phi 2, and phi 3, and this one is a total ignorance. Total ignorance. So we get this transformation matrix, and of course the transformation must be equal to 1. This makes the redistribution is equal. Okay, once this transfer matrix is available, we can do some belief redistribution to transfer the mass, the beliefs of in the different frame to a common frame. Okay, do something like this. But how to calculate the parameters in the matrix? We use we consider, okay, because after the transfer, okay, they will be combined. Combined, we just use the DS rule. Combined, the combination result, we can get the BTP, pygnistic probability, and calculate the pygnistic probability, the difference between the probability and the truth, and then we can get the error. If we make the error is as small as possible, we can get these parameters. By the optimization, we can get these parameters. So we use the some optimization method to calculate the transfer matrix, the parameters in the transfer matrix. And of course, if we do some, because in fact, I think the mainly contribution is about the transfer matrix. We just consider, for example, the theta 1 is just considered related to the phi 1, phi 2, and phi 3, and this replaces the set of phi 1, phi 2, and phi 3. This is dependent on prior knowledge, unlike the training data. we do the other sets will be considered 0. And of course, this is ignorance. This is used to control the total ignorance, like the weight and the total as ignorance about the transformation. So this is a very particular structure about the transformation. By doing this, we can reduce some many unuseful parameters. We just keep some important parameters. A lot of parameters are considered 0. If we consider all of them, the computing burden will be big, and it requires a lot of the training data or label data, because in many cases the training data is not so much. So this is the classification result. We found that use our method that we can also significantly improve the classification accuracy, because we use a very few labeled data to get this combination result. Okay, I will get a conclusion. At first, we present some classification method with the adaptive imputation of the missing value. This is about the incomplete pattern classification with the missing value, and we designed a strategy to estimate the missing value. If the missing value is not so important, we will do the direct classification. If the missing value is very important, we will do the estimation of the missing value. After that, we will do the classification. And the second one is the evidence-based weighted fusion for the transfer classification of the heterogeneous data. For the transfer classification in the heterogeneous data, we allowed for each data in the target domain can have multiple mapping value in the source domain. The multiple value can reflect the mapping uncertainty. The classification result with the different multi-value are combined by the evidence theory. And we also propose a method about the combination of the transfer classification. When we have multiple source domain, and we consider each source domain should be used to help us improve the target. So for each target, we can get multiple classification result corresponding to the multiple source domain. Then the evidence combination rule is used to combine the classification result. And there's also refined reliability evaluation is used in using neighbors to reveal the classification errors about the classification. And for each object, we will calculate its reliability evaluation matrix to correct the classification output. And after that, we will do the combination for different classifications. This can significantly improve the classification accuracy. And also, this is still an open problem for the classification with different frames. In fact, this is still a difficult problem to solve. And in the future, I think we want to combine the build functions with the deep learning, because deep learning developed very fast in recent years as a core of artificial intelligence. So we want to combine the build function with deep learning, and how to, in the deep learning network, use the build function to characterize the imprecision and uncertainty of the classification. And we also want to extend the build function to the multi-model data to improve the fusion performance. Because now the data is very multimodal, like some image data, some signal data, and some text data. And how to use a B function to combine them efficiently. I think it's very interesting to do in the future. And we also want to carry out application of B function in some unknown target, like the open set recognition, to extend the application of B function in some new case, like the open set. Now with the classifier usually consider the closed frame. The object must, the class of the object must lie in the frame. In some real applications, object may not belong to any of the class of the frame. So this can consider open set recognition. This is some reference about work. Okay, thank you.